So conics. There is our definition of a conic. It's very similar to the definition of the parabola, you may remember. It's the locus of points whose distance from a fixed point, which we call a focus, is a multiple, and that multiple we call the eccentricity of its distance from a fixed line, the directrix. Now, what we saw in extension 1 was the parabola, where we didn't say a multiple, we said it was equal to the distance. And that's because the eccentricity of a parabola is 1. So that multiple is 1. The distance is the same. The conics, or the conic sections as they are known, can all be found in the cone itself. If you slice a cone horizontally, then the shape you will get is a circle. A circle has eccentricity 0. Okay? Its focus, I guess you could think of as the centre of the circle, but you don't have a directrix. So. Now, if I slice at an angle, voila, we won't get a circle, we'll get an ellipse. It's important that slice, though, doesn't go through the base. As long as it doesn't go through the base, we will get an ellipse instead of a circle. And an ellipse will always have eccentricity less than 1, so between 0 and 1. Okay. If I slice, and this is really dodgy pretend here, but it was hard to draw it, parallel to the sides of the cone, trust me, that slice is parallel to the side of the cone. It just looks like it's not. It's optical illusion. Then we get our parabola. And as I say, its eccentricity is equal to 1. And if we slice straight down, we get our hyperbola. And a hyperbola has eccentricity greater than 1. Okay, so let's have a look at our ellipse. Ellipse, as I say, has eccentricity less than 1. We're going to derive the equation of ellipse using our definition that we just had. So it will have a focus, which I've called S. And it will have a directrix. And that point of intersection I've called Z there with the x-axis. Now, we just said the distance to the focus is equal to a multiple, that multiple being E, or eccentricity, its distance to the directrix. So looking horizontally, the vertex here, which I've called A, the distance AS will be the eccentricity times the distance A to Z. But the other vertex, also its distance from S, is also equal to the eccentricity of its distance to Z. Okay. Now, if I combine these two ideas then, have a look at SA dash plus SA. Well, that must be the width of my ellipse. So I know that'll be 2A. SA dash minus SA then, using our definition of the ellipse, I can factorise out the eccentricity as a common factor, but it'll be A dash Z minus the length AZ. See, I've tidied up this A dash Z, sorry. So A dash Z minus AZ, so A dash to Z minus AZ would also be 2A. So SA dash minus SA is 2AE, SA dash plus SA is 2A. Now we can do our simultaneous equations. Add them together and I get that S to A dash is A1 plus E. Subtract them and I get that SA is A1 minus E. Okay, so the focus, the distance from the centre to S, because basically that'll give me the x coordinate of the focus, would then be the distance from O to A minus the distance from A to S. O to A is A. We just said that S to A is A1 minus C. We get a lovely little expression, simply AE. Now, you don't have to derive this every single time. I'm just showing you where it comes from here. So the focus is simply AE. Whatever the vertex is times the eccentricity. And as I said, there are actually two foci, and they are symmetric. So the other one would be minus AE, 0. Let's get an equation for the directrix then. Distance from O to Z would be the distance from O to A plus AZ. So we get OA plus SA over E. Again, playing around with our definition that we saw before. Remember, we said SA was equal to E times AZ. So I get AE over E, just making sure we got a common denominator of E there, plus A 1 minus E over E, and look at that, it becomes A divided by the eccentricity. So whilst it looked very complicated how we got those answers, the final answers are nice and neat and very easy to remember. Right. So the directrices turned out to be plus or minus A divided by E. So focus A times the eccentricity, directrices A divided by the eccentricity. Okay, so focus AE 0. Now let's find out an equation for the actual ellipse itself. There's our random point P, which I'll give coordinates x, y. Drawing in a few lines here. Horizontal one going across to the directrix. If it's horizontal, it will have the same y value as P, so I've given it the y value of y. It's on the directrix, so it'll have the same x value as the directrix, so it's A over E. They're the coordinates of n. Definition of ellipse, the distance from P to the focus is equal to the eccentricity times the distance P to the directrix. Distance formula, let's sub all that in. Tie these up quite nicely because we get things like y minus 0 and y minus y. So I've got x minus AE squared plus y squared is E squared x minus AE all squared. Expand the whole thing out. It's getting closer. Collecting the x squareds together, the y squareds together, and anything by itself. Going to divide everything by a squared 1 minus e squared. The reason we do that is unlike the circle, where we normally see it as x squared plus y squared as the radius squared, the ellipse we normally always write equals 1. So we always divide by, if you like, the radius squared. So I've divided by the a squared 1 minus e squared there. And we get this formula, x squared on a squared plus y squared on a squared 1 minus e squared is equal to 1. But we know that when x equals 0, the y value would be the b, the plus or minus b we said. So when I sub that in, it actually turns out that b squared is in fact equal to a squared 1 minus e squared. So we get a far more neater formula. So for an ellipse where the a value is bigger than the b value, okay, there's our ellipse. X squared on a squared plus y squared on b squared is equal to 1. Simple as that. B squared is equal to a squared 1 minus e squared. Focus will be plus or minus AE 0. Directrices plus or minus A divided by eccentricity. Now, sometimes an easier way, because they might ask us what is the eccentricity, and we're meant to use this formula, b squared equals a squared 1 minus e squared. It's sometimes easier to remember this with e squared as the subject. E squared is a squared minus b squared over a squared. You just bang, sub that straight in. Because if you've got the equation of the ellipse, you're going to have a squared and b squared straight away. So you sub that into e squared and away you go. Some terms, we don't have a radius in an ellipse because it's not consistent like the circle. So we have two, for want of a better word, radii, but we don't call them radii. We call them the major semi-axis, so the longest radius, if you like, which would be a units, and the minor semi-axis, which would be the b units. So a and b are the two semi-axes, axes, whatever the plural is. Now, if b is greater than a in that formula, what it now means is the foci will not be on the x-axis, it'll be on the y-axis. And so the ellipse will be elongated vertically rather than horizontally. So if b is greater than a, as I say, the foci is now on the y-axis. Instead of b squared being a squared 1 minus e squared, a squared will be b squared 1 minus e squared. So basically your x and y's are swapping around. So a's and b's swap around. The foci becomes 0 plus or minus be. And the directrices become plus or minus b divided by e. Area for an ellipse, pi AB. It's another reason why the area for a circle is pi r squared. Because its major semi-axis is the same as its minor semi-axis. So it's pi r times r, pi r squared. So it actually comes from the formula for the area of the ellipse, which is pi AB.
Do we have to know how to
Derive the formula? You can do it via integration. Now that we know how to find areas under curves, it's very easily done via integration. All right, that's enough of the theory behind it. Let's find the sorts of things that they're going to ask us to do. I think the questions in the HSC are broken up into 2 bits. There's like the basic definitions, so you know how to find a focus and directrix and things like that. They're, I guess, if you like, the gift marks. So, and they'll usually be, I would consider an easy one. And then there is, like we saw in parametrics, the locus type question at the end. And that's usually the harder one. You tend to see both. Okay. Our formula here is x squared on 9 plus y squared on 5 is equal to b. A squared is bigger than b squared, so we know our ellipse is elongated horizontally. All the important features. A is 3. The eccentricity I can work out. E squared minus b squared on a squared is 4 on 9 is e squared. So the eccentricity is 2/3. What else does it want me to find? I found the eccentricity. The foci, well now I know the eccentricity. Foci is simply a times e. 2/3 times 3, that's 2. The directrices, a divided by e. 3 divided by 2/3 becomes 9 on 2. There's our directrices. Let's draw it. Going to draw it using a method called the auxiliary circle method. Reality is you probably won't draw it this way. You'll probably just get your template if you've got one and go, ooh, there's an ellipse. But to draw an accurate ellipse, there's this idea of the auxiliary circle. And we draw in the circle, same radius as the major semi-axis. So in this case, 3. Okay? And that ratio, b on a, becomes important. √5 divided by 3. And basically, all we do is we can slide a ruler along and we just mark off that ratio times the distance from the axis to the circle. So in this case, I would have measured to here. It would be however many units on my ruler. Say it's 3 units, worked out perfectly. I'll go 3 times √5 on 3 is √5. I'll mark off √5. And I just do as many times as I need to slide the ruler along. Whatever that measurement is, times √5 on 3, that's where I'll mark a point. By symmetry, it'll be the same below, but then on the other side, it'll also be the same. Another vertical line. Okay. It is highly unlikely that they will ask you to draw an ellipse this way. But this is how it works. And you get a lovely, if you want a lovely sketch, that's how you would do it. Once upon a time, they used to ask you to do this. Don't know why they stopped asking that question. Hey, maybe they'll do it again this year. Voila. There's our ellipse. Okay. Hey? So I'll just mark in the points. There's our foci. There's the dream. So you'll notice with the ellipse that the foci are inside, just like the circle. And the parabola also has the foci inside. And the directrices are on the outside of the ellipse. Okay. Its major axis is 6. Make sure you read the question carefully. Major semi-axis is what the radius is like. Major axis is the whole diameter, if you like. So it would be 6 units. Minor axis, 2√5. I see an equation like this. I notice that it's x squared and y squared. My first thought is, oh, it's a circle. But the coefficient of x squared and y squared are different. So therefore, it's not a circle. They're both positive, so I know I've got an ellipse here. Going to have to complete the square in order to find the correct one. But of course, in order to complete the square, I like my coefficients of x squared and y squared to be 1. So I've created some fractions here. I've divided everything by 36. So on the top of the fractions, I can now complete the square because I've got a coefficient of x squared being 1. So everything was divided by 36. Why did I choose 36? Well, 9 fours are 36. So that got the coefficients that I wanted. So on the top, I get x plus 1 squared. And for the y's, I get y minus 2 squared. But that means I've got to add to the other side 1/4 and 4/9. And you'll be amazed when you add 11 on 36 with 1/4 and 4/9, what you get. Oh, it's 1. That was lucky. So I don't have to do anything more. Now, of course, if it didn't happen to magically turn out to be 1, which of course is what we want, then say that turned out to be, oh, I don't know, 3. Then obviously I just divide everything by 3 to make it 1. I mean, it needs to be equal 1 because our general formula was x squared on a squared plus y squared on b squared is equal to 1. I need it to be equal to 1. But we've got some sort of shift happening, just like we saw with every other shape. So the centre of this ellipse, instead of being at 0, 0, is at -1, 2. B squared is bigger than a squared, you will notice. So this particular ellipse, if we were to draw it, would be elongated vertically rather than horizontally. So it's the b squared I'm interested with here, not the a squared. B squared is 3. B squared is 9, which means b is 3. My eccentricity squared will now be b squared minus a squared on b squared, with the a's and b's are swapping around. And I get √5 on 3. So my foci, I would go b times e, which is √5, but remember, we've got a shift happening. So I've shifted it -1 up 2. So the foci of this would be -1, 2, plus or minus √5. And the directrices, they would now be horizontal lines, but we've shifted them up 2 as well. So it's b divided by e, shifted them up 2. No.